we spoke about how to differentiate polynomials. In other words, how do I differentiate x to the power of 4? The technique ends up being dropping the 4 down and having a 3 instead of 4, right? So it's 4x cubed. And the reason that worked is we verified using long division. Do you remember that? We verified what is the formula. And it's very easy to remember if you read or listen to Oscar Wilde's story. It's encoded in here, right? So you have the nightingale, and it begins with power 3. And it gives the powers 1 by 1 to x. So you can see how to factor difference of 4 powers. In general, I can just figure out how to factor difference of n powers. It ends up being z minus x times z to the n minus 1, x z to the n minus 2, x squared z to the n minus 3. Do you see how z is giving away its strength, its power, to that rose x until z is no more, it is gone. Good? So you will not forget it. And then it's easy to verify that this formula, once you notice the pattern, it's easy to verify that this pattern is true. Here is that verification. I multiply by x, I multiply by z, I carry the algebra, and I see that this formula is indeed what multiplies z minus x to form z to the n minus x to the n. And from there, we have that the derivative of x to the n, where n is a positive integer, is just simply n x to the n minus 1. So far, so good, yes? Beautiful. If anything, guys, you ask me questions, you try to talk to me, I will do my best to explain if something is unclear. And here is that calculation carried out. So I just carry out the calculation simultaneously for all the powers of x, for x squared, x cubed, x to the 4th. That's what I do when I derive this property. So I observe factoring z minus n, z to the n minus 1, x, z to the n minus 2, and onwards, right? And then once I cancel z minus x, I can take the limit. That will be x to the n minus 1. This will be x times x to the n minus 2, or again, x to the n minus 1. Each of those summands in the limit is x to the n minus 1 by continuity, yes? And how many terms do we have here? We sum from 0 all the way until x has all the powers. So from x to the power of 0 all the way to x to the power of n minus 1. That is n minus 1 plus an extra term, which is n. So we have n x to the n minus 1. That's why the formula is true by definition, but I did the definition once, so now I know the formula. And that means that the derivative of x to the 6 without any complicated calculations is simply 6x to the 6 minus 1, or 6x to the 5th. The derivative of x to the 101 is 101x to the 100. Derivative of x to the 30 is similar, yes? So we now have our first shortcut. Then in order to finish off polynomials, I need to know that derivative of a constant is constant times the derivative. Now, let's see a quick comprehension check. Very quick comprehension check. If I have the derivative of 5, the derivative of the function that identically equals to 5, that will be what? Without any calculations, that will be what number? You understand? We have the function equal to 5. So f of x equal to 5. The derivative is derivative of 5, of just 5. The derivative is, yes. Now, wonderful that you say it's 0, most of you. I think one person by mistake maybe wrote 5x. The derivative of a constant is 0. Why is that the case? It's very obvious. You understand? What's a constant? A constant is a horizontal line. Do you agree? Constant is horizontal line. And when I ask for the derivative, I'm asking for slope of a horizontal line, which is 0. Yes? Very obvious. One other very simple question. Now, if I find that the derivative everywhere, so anywhere I look, the derivative is the same number. For example, anywhere I look, the derivative equals to 5. Then the curve looks like a what? You understand? So the curve is such that whenever I look anywhere, I find that the derivative is 5. Straight line, beautiful. Straight line that has what slope? Yes, Pavel, it is 5x, possibly 5x lifted up or down or shifted. Doesn't matter where, because you see, geometrically, look at it, guys. I can move my line to the right or to the left, up or down, and that will not affect the slope where I zoom in on the curve, right? So moving the curve left or right, up or down, does not affect the slope of this curve, okay? So the image that you should all have in your mind when you think of derivatives, the image should be something like this. Let me draw it for you, right? So a differentiable function is one that looks like it's made of microscopic, tiny line segments. Not like I drew, you see, notice I drew them in a way that you can recognize the line segments, right? What it is that you zoom in and you see a line. So the image you should have is microscopic line segments attached to one another. So you see that slopes here are not going to be aligned. The derivative is not constant. That means that this is a bent curve. That's in fact how you simulate curves in the computer, or how you simulate fabric when you play video games. You just, you build up fabric out of chainmail, out of triangles. Okay, that's the two-dimensional version. Triangle is part of a plane. It's a two-dimensional version of line. Does it make sense? Please silence your microphone, guys, if you are not answering a question. And please also pay attention to the lecture. One second, I'll just try to find where it happens. It's not so, for some reason it doesn't jump right up. Where the hell is this? Here it is, found it. Zohaib, please pay attention in class. It's not the best time for communication or conversations, right? I will, guys. You see, so some people log in and then I'm sure not participate in this class. I will make sure that you know the material. And I would hope that I will not have to do that using a very unpleasant way for you, and unpleasant to me. I will interrogate you. Understand how it's done in Russia? Interrogation. I ask you 3 questions. If you don't answer those questions, I presume you do not know anything. I don't want to get to that point. So I hope I frighten you, but not too much. You enjoy coming to this class, you enjoy the material, but if you do not, I will frighten you. I will come and hunt you during Halloween. I promise you. Yes, well, I don't look too scary enough, right? That's how you get to people, right? You are not scary, you come close and closer and closer, and they don't run. And then it's too late. That's how I get them. Okay, then my idea is, this is a line. It's a chain of line segments. Of course, if you zoom in at whatever looks like a sharp edge, it will also look like a line. You see, between any two links in the chain, you see always more links. So it's kind of not easy to draw, or maybe impossible to truly draw, right? It's what you call infinitesimal lines. But infinitesimal, it's a weird type of concept. But it's a very good analogy. Good? So if you find that the derivative is 0, that means you're dealing with a horizontal line. If you find that the derivative is another constant number, that means that the links in your line chain, in the chain of lines, are all aligned to make it one global line. Yes, that's pretty natural from this point of view. Cool. So let me ask you, what about the derivative of a constant times the function? Why isn't it 0? So let's say I have 5 times the function. I take the derivative. I'm sure some of you would have said, well, it's 0. Why? Is it not 0? Or maybe it's correct to say it's 0. Right? The derivative of 5 is 0. Right? What about the derivative of 5 times f of x? Does it, there is a 5 there. Does it mean it's 0? No, it does not mean it's 0. Why? Because 5 times a function, 5 is just part of it, but 5 times a non-constant function will not make it will not make it a horizontal line, right? If it's 5 times 1, sure. But if it's 5 times x, it's not a horizontal line, right? You change the point of x and then you have a different value. It's not a horizontal line. The derivative is not 0. Make sense? So a non-constant function cannot have derivative 0. That's going to be important in just a moment. Everybody understands? Well, Muhammad, how is it not 0 again, right? What is it? So if a function is not constant, right? So look at it, right? If I have 5x, it's 5 times a function, right? The derivative of 5x is just 5 because well, that's the slope of this line, right? But the derivative of 5 by itself is 0. So make sure that you understand why constant times a function is not necessarily a horizontal line. And if it's not a horizontal line, if it's not a constant function itself, and then the derivative should not be 0. Good? That's very intuitive, right? So I just mentioned it because I do see that all the time. So the actual property is this. If I take derivative of a function multiplied by some other scalar, I can just factor the constant and just take the derivative of the function. It's c times the derivative of f. You can actually think of it geometrically. I will teach you if you want today to think of it geometrically, okay? And you can also think of it in terms of definition, but make sure that you understand both perspectives. Similarly, the derivative of sum is the sum of the derivatives. The derivative of the difference is the difference of the derivatives. I put it as law 3, but really it's obviously following from law 1 and law 2. All I have to do is I have to take function f and plus function g multiplied by minus 1. Okay, so it immediately follows from 1 and 2. In fact, again, subtraction is very similar to addition. Usually no need to separate them. Okay, so here is the proof. Here is the proof formally, right? I use this notation 1, I call it. So the derivative of this function is just this function evaluated at z minus this function evaluated at x. I can clearly factor out the c here. And then I can take limit of a constant, and as z goes to x, constant doesn't care, yes? And then I multiply it by the limit, because remember, limit of a product is product of limits. And the limit of this expression, I recognize its shape, you understand? This is what you call formal reasoning. The limit as z goes to x of f of z minus f of x over z minus x is f prime x. I hope you understand and it's not empty noise to you guys, yes? This is just a recognition of what this derivative is. This is secant slope. And when I slide one point, the point z f of z, I control it by making z go to x. I make the 2 points merge, and that becomes the slope of tangent. Very simple. Good. Now, what about the derivative of sum? So this is my function. If you prefer, give it another label. So this full function is evaluated at z minus this full function evaluated at x, and I take z going to x. So then what I do is I separate, I group together f's, and I group together g's, yes? And then I see that it's the sum of 2 fractions. Here is one fraction and here is the other. The first fraction is obviously the derivative of f. Second fraction, obviously the derivative of g. Good? So the limit is clearly prime of first function plus prime of the other function. The 3 is an obvious consequence of the previous 2 results. I hope you understand. When I say obvious consequence, guys, here is what I imagine some of you are doing. So you might have a faint understanding of some idea. You go home, you don't practice it. The faint understanding is like a dying ember. Whatever was burning in it is quickly extinguished and you know nothing of the subject. You should think, almost like a paranoid person, think about it and solve it again and again and again until it's completely obvious in your mind, until it's second nature. So if it's second nature, you cannot be bullied, you cannot be scared, you cannot give me wrong answer. You're not drowning, right? So yes, that's how it is in Europe. In Europe, it's called oral exams. You are interrogated. So, and not always in a pleasant way, right? So people ask you to pick up a question, or they ask you a question, and it's kind of like an interrogation, and they verify whether or not you know something or not. And that's truly It's time consuming, but it's truly a great way to control cheating, right? The only reason I don't do that as often is it's a waste of my time, right? So, but I will do it, of course, for people that rub me off wrong. So this is the derivative of a polynomial. Do you see? It's a polynomial. Now using those laws, I can very quickly, derivative of constant is 0. Derivative of minus 5 times x, it's simply, I can just take the derivative of x and multiply by minus 5. Derivative of 8x cubed is 8, derivative of x cubed, and onwards, yes? You understand how this works? And I get very quickly this answer. I don't need to go through long-winded definition. Again, guys, let me see, quick comprehension check. As quickly as you can, please type for me what's the derivative of this example. 10 minus x squared plus 7x cubed. Quickly calculate derivative and tell me in the comments. Yes, great. You don't always have to write the 0, guys, right? So you just write the solution. So for example, if this were a question on the exam, right? Calculate. Some of you might be terrified and might start doing way more than you have to. When I say calculate, I just mean here is this polynomial. Any means are okay. Just give me the derivative. You don't have to go by definition. If I said calculate by definition, that means you have to do it by definition. So make sure that when I give you the exam, you go by instruction, and you have practice exams. Make sense? It's good, of course, to practice and do it by definition until you're absolutely convinced that you understand how the definition works, why it makes it true. And we are actually going to check that understanding in a few moments. I hope you have this, you're tense and you are excited about what's coming.
Oh, wait, quick question.
Go ahead.
So I understand the process, but what's the, what will you use this for?
What do you use what, to take the derivative?
Yeah.
Well, we spoke about it a while, right? So again, as I mentioned, always think, what is the derivative? Why was it interesting to anybody? So the most immediate answer is we can solve using this idea, the instantaneous velocity problem. So when you're driving a car and somebody snaps a photograph of you driving in the car, in the photograph, if it's high resolution, everything is still, yes? But there is some indication of you still moving, and that would be your speedometer, right? The speedometer is pointing to something. Maybe the speedometer is pointing to 0, so you have velocity 0, yes? Or it's pointing to 60 miles an hour. That means you're driving at 60 miles an hour. And using this technique, you can, even without seeing the speedometer, figure out what the speedometer is if you have a recording of you driving, let's say, in a straight line, okay?
Okay.
So that's instantaneous velocity, right? In other words, you need to understand velocity if you want to understand how things are moving about. And more deeply than just the velocity of a car, you have, if you read physics, again, guys, right? If you want to understand the use of that, you need to study something more. You have to have a certain goal. What's the goal? Do you want to understand how the universe works, right? Maybe you want to understand it globally, or maybe you want to understand it locally. Right, so calculus is used everywhere from probability theory, for whichever describes the motion of the tiniest particles, to globally describing the motion of galaxies. Okay, so you can. I will show you I showed you where you have that physics book, right? You can start trying to read it and see if that's an interesting goal for you. So one thing about Newton's laws, Newton's law was considered fundamental law, the most fundamental law, in fact, until early 20th century, until revisions in quantum physics that were almost simultaneously created, and the theory of relativity, right? So by Newton's law, a particle that does not experience a non-zero net force. In other words, if a particle experiences a net force of 0, will move in a straight line. Does it make sense? The particle will move in a straight line. And if it were traveling on a curved path, let's say if you have a shuttle and you are traveling on some trajectory, if you launch a satellite from that shuttle, the satellite no longer experiences any force, and it will travel tangentially to the curve, to the trajectory of your rocket. Okay, do you understand? And then so all sorts of other things. The more advanced things, if this is not exciting, you have to understand that mathematics progresses in a very, very strange and convoluted fashion. You understand? So there are many problems that do not appear to have anything to do with the slope of tangent line, but they are related to it. You see, through a long chain of reasoning. I don't know. Do you follow me, guys? Right? Some of you look like, my God, well, I don't care. Yes. Well, it's too bad if you do not, guys. It's very sad for me. You are missing poetry. Your life is not worth living, almost. If you don't feel that, so it's less full. Yes. So here, guys, here is the next question. Let's see how well you understand anything. This is the solution, right? So the solution is minus 2x plus 27x squared. My next question is, what is the derivative of 2x? Zohaib, by the way, Zohaib Manzoor, are you back from your conversation or not yet?
No, I wasn't having a conversation.
Okay,
When I use, okay. If you want, I can talk about it, but I'm back.
No, I'm sorry. I just sorry if I pick on it. I just try to scare my students to be here. That's all, right? So hopefully not too much. Hopefully excitement is what keeps you here. But if not, then it has to be fear, right? If not love, then fear. But thank you. Glad that you are with us. What is the derivative of 2 to the power of x? Come on, guys. You do, and again, when I ask you to calculate this derivative, you can decide what you want to do, right? My question is calculate it with any particular way you possibly can. Okay, Rafid, great. X times 2 to the power of x minus 1. One person bravely stepped forward and answered. What about the rest of you? And guys, one thing is that you see, you are possibly from school, you are trained like circus animals to spit out something, solution. You think if I ask you a question, you think, well, the answer must be 7 or 12 or some sort of thing like that. But what I ask you is, well, reflect on this question. Here is the derivative of 2 to the power of x. Reflect on the question. Okay, so Pavel says 2 so, and by the way, make sure you write it in a way that it's nice for me to see. So maybe you have some sort of grammar issues there, right? 2 to the times x to the power of x minus 1. Oh, wonderful. Okay, so more people are joining. Pavel is saying something great. What about the rest of you? What are you saying? Well, Zohab, that's fine. So, guys, I'm pushing you a little bit, but I hope you are not going to allow me to push you too much, right? I hate that about people, that they listen to somebody saying something, right? Maybe I'm a liar. X to the power of x minus 1. Okay, for interesting. Ikra, I don't know what it includes, right? Just use your thought. Okay. I just want to see your reaction, guys, mostly than anything. Okay. I want to see your reaction. That's all I want to know. Okay, so that's it. We have your answers. Let's now solve it together. Good. I've seen many answers here. What about Carolina? Did you say something? And what about Minkowski? Do you say something? Okay, interesting. You don't have to again, right? Just I want to. I'm just when people hesitate, I wonder what causes the hesitation.
I think it has to include something with logs or natural logs.
Maybe, right? So let's do it this way, right? So are you ready, guys? I'm going to use my thingy, my what is it called, stylus, and we will calculate it together. Yes. So look at it. We have the power rule. We have 2 to the power of x. Yes, power rule. Yes. Yeah, how could I not notice the power rule? Come on, right? And then what I do is this. When I take the derivative, I just simply drop the x, and I have 2 to the power of x minus 1. Isn't it simple? Yes? So incredibly simple. Did you understand it in the comments? Please write to me that you understood. If yes, if you followed it. Right? Understood or yes or something. I want to see how well you follow my instructions. Yes, yes, yes. Zohib, yes. Oh, Julia, wonderful. I understood it better. Whoa, I'm so glad I explained it so very well. Anybody else? Did I? Yes, sir. Yes, Heidi. Yes, I want to see more. Come on, everybody understood? Everyone? At least I understood. Yes, oh, I'm so glad you understand it so very well. Because I lied to you. It's a completely stupid, ridiculous, and incorrect solution. So wonderful that you all understood it, because it is wrong, terribly wrong, stupidly wrong. But you believe me. Why? Because I am your instructor. That's exactly what happens today. If you follow, I receive such disgusting. My God, I'm seething with irritation, right? About what happens in debates, what happens in how people react to anything, pretty much, right? What happens in Israel with the lockdown, right? Because the expert said, I believe in science, right? That is pretty much what you do if you do not use your gray cells. Of course, I badgered and bullied you to say that you understood, right? But my point is, do not believe me, especially me, who is a very, very, sketchy person. You know where I come from Eastern Europe, right? In Eastern Europe, you are like the slimy fish if you survive. Yes. So it is absolutely inapplicable, because why would the power rule work? Okay, guys, right? So you said right away you applied the power rule, and I think I'm not sure how much am I entering into your soul, right? But you applied the power rule without understanding. And a great expression is that you will see. I don't know. I'm not sure if it would affect you, but maybe it was Einstein who said it. Maybe somebody else. Verständige Leute kannst du irren sehen in Sachen, nämlich die sie nicht verstehen. People of understanding, you will see make mistakes in things that they do not understand. Yes? This is, and here is the mistake, as it appears to me, the mistake that you have made. Look at it. Here is x squared, right? X squared and 2 to the power of x. To confuse between them is like to confuse between this face and that face. You look at it, right? Here, the base is variable, but the power is fixed. Here, the base is fixed, but the power is variable. It's a very different function, just as this person and this weird other guy are entirely different people. And when you confuse between those two things, this is what I think of you. This is how you appear to me. Do you understand what it is? I didn't bother drawing it for too long, but I hope it is absolutely clear to you. So don't let me confuse you with this thing, okay? I used to paint, but those are crappy drawings. I should show you my better drawings, right? I'm not sure if I can still do it because I stopped at 16. Those are, if you say artist, my God, you're too nice. Those are crappy drawings. I need to prove to you how I used to draw. Right? Maybe I'll open my phone, right? I have one thing there. You see, you stroke my ego. I used to have a big one. Right now I just have a shell of that ego. 1 second, guys. Here, can you see this? That is the last thing I drew when I was 16. You see that? Since then, I haven't been drawing much. I still have some other kind of caricature drawings, so that's one I tried. Yeah, not too bad, right? 1 second, guys. I will just. How much? Very nice. Yeah. Say goodbye to my cat, and then I am back with you. I wish. I do not know if I had a minor stroke or what it was, but again, what I still do is it's very dangerous to drive. You know why my drawings are not always finished? It's like a ghost takes over you. I still have very, very vivid dreams, and you kind of draw it without even noticing, right? And then the vision is gone. And my visions are leaving me slowly as I get tired and disappointed, right? Or they are just haunting me at night. That's when I see things. I'll show you my nightmares. You are very often part of them. Okay, so let's talk about exponential maps. Are you with me, guys? Yes? Wonderful. Strength and honor. So guys, we are talking about exponential functions. Bear with me, it is a difficult topic. It is, you think about it in entirely different ways, not like you learned in school, okay? So first of all, quick review of exponents, okay? So remember what it means to have a to the power of 3. This is just a bookkeeping of a times a times a. And in general, a to the power of n, when n is an integer, it's a times a times a, n times, yes? Now, you have this exponent addition law. For example, if you take a cubed times a squared, you realize that altogether you're multiplying a by itself 5 or 3 plus 2 times. You agree? That's what it is. It's a review here, right? And in general, if I have a to the power of n times a to the power of m, I just realize that I multiply a by itself n plus m times. Good? Now, where does, I didn't bother writing it here since it was not immediately necessary, but let me actually still do that as I did for the other class. Well, what about this, guys? What about if I have, let's say, a to the power of 3 divided by a to the power of 2? What do I notice? This is a to the power of 3 minus 2. You agree? Yes? You understand what because I used to have 3 powers and the powers of the denominator annihilated the top, right? And that's how we have the difference law. Yes. Now, if I were to do it the other way around, right? If I were to do it the other way around, we get what? We get, let's say, have a squared over a cubed. What do we get? If I want the law to work, the exponent law to work, I get a to the power of minus 1. Do you agree? But a to the power of minus 1, it's not, it's 2 minus 3, it's minus 1, yes? But what it means that 1a survived in the denominator. That's where I have 1 over a. Isn't it obvious? Now you see why raising to a negative exponent, we will have 1 over raising to the positive exponent. It's because of that. Good? Now let me quickly test your comprehension. Tell me and explain why, let's say, what is, let's say, 2 to the power of 0? What is that equal to? And of course, why, which is more interesting to me. So Fu, Alan, 2 people already gave me an answer. What about the rest of you guys? 2 to the power of 0. Why? Why? Right? If you just memorized it in school, I could have made you memorize an entirely incorrect fact, and you would have kept with it and hoped to survive this class, right? And maybe, you know what it happens when kids are very young, they don't think critically. Whatever is fed to them, they remember, and they imagine that's to be the truth, unless you're, of course, a particular personality, right? So you imagine that whatever you learned in school is truth, even if you did not care about it. It actually affects your values, which I see that it's pretty terrible, right? To be affected by your values, what you believe in, to be affected by school. Not good. Should come from your heart, from your mind. Why 2 to the 0? Look at it. We talked about. I gave you a pretty big hint. What is 2 to the 0? It is a code. Something happened. What happened? How do you get 0? Do you understand why 2 to the power of minus 1 is 1/2? Yes? Do you understand why 2 to the power of minus 1 is 1/2? What made it to be true? That's dangerous thinking. What is 2 to the power of 0.01? That's taking roots. That's not that might be a way, but then you have to, Christian, you have to know how to take roots. It's something much simpler can be said here.
Well,
Yes.
the way I see it, right, is that let's say you have like a times table, right?
Mm-hmm.
And in those times tables, right, let's say you included 0 in that times table. So I think about it like this, right? You got 0, then 1, 2, 3, right? And then you're doing the multiples of 2 within that times table.
Mm-hmm.
So if you do it to the power of 0, right? 2 times 2 to the power of 0 is still gonna, the answer will always be 0, right? But since it's to the power of, it's still, the answer should still be 2. Because if you do it to 2 to the power of
I'm
1.
sorry, James. You see, I misunderstood your sentence. You said the answer first will still be 0, then you say it still will be just 2. I misunderstood your construction. What do you mean?
So
2
like,
to the power of 0, first of all, is what number?
so 2 to the, so put it like this, right? We put it like this, right? So 2 to the power of 0, right? We know that if we include 0 in the times table, right?
Okay.
2 times 0 will always equal 0, right?
Yes, but 2 times 0, yes.
Yes, 2 times 0. Yeah, that will always equal 0, right? But it's like, it's almost like a pattern. So if you do like 2 to the first power, right? That will equal, never mind, forget about it.
Well, thank you for talking. So sorry. I hope you did not feel intimidated, by anything here. I really appreciate that you speak. Okay. So
Okay.
again, guys, right? First of all, James reminded me. I wondered, do you remember why 0 times anything is 0, right? It should not be just, somebody told you, somebody says so, right? 2 to the power 0. Again, let's look at 2 to the power of minus 1. You see, so this is where imagination comes in. I think of what? I think you have numerator 2's and they were fighting with denominator 2's. Yes? So how could 2 to the power of minus 1 be accomplished? That could be accomplished by, let's say, 2 to the power of, 1 minus 2. You agree? And what does this mean? That means, based on previous notation, that I had 2 in the numerator, and this 2 on the numerator was jumped by 2 2's on the denominator. Yes? It was jumped. And he lost, right? He lost honorably in this combat. The 2 in the numerator annihilated one of the 2's of the denominator, right? It's like, oh, I'll destroy you. He destroyed one of the 2's in the denominator, but 1 2 in the denominator survives. Yes? Are you following me? Guys, right? It's not just I'm explaining it to myself, right? You understand why. Yes? Now, what happened if I have 2 to the power of 0? By this analogy, what happened here? You're asking yourself what story, what you're looking at crime scene, and you're asking what was actually going on. What was going on? What might have been going on?
Oh, they just didn't they just put like 2, like the same thing like you did? They just put 2 under 2 over 0, and it was still equal.
Well, careful, by 2 over 0, right?
Or
So what I did over here, I said, how do I get -1? -1 is that 2 to the 1 minus 2. You understand? Division makes a minus. Does everybody remember or understand that that if I put that minus seems to correspond to division, right? So it's in some sense when people say mathematics is a language, what they mean by that perhaps is that when you look at a formula, a story comes up to life perhaps, and maybe not one story but many stories. That's what's interesting about mathematics. It can narrate many stories simultaneously. Yes. So the story that I thought about here when I see -1 on the power of 2, I think and I think that somebody survived here, right? Somebody in the denominator survived. Do you understand why, guys? Again, right, let's look here. If I have 2 to the power of 1 divided by 2 to the power of 2, right? The notation that it's I do not know if that makes, I'm not sure if that makes sense to you. Let's say I have 2 to the power of 3 divided by 2 squared, right? What did we have? We have 2 times 2 times 2, 2 times 2, yes? And we can cross away this, right? What survived? What survived is just 2 to the power of 3 minus 2. Do you agree? Because it's 1, right? 3 minus 2 is 1. You notice that when the numerator power is bigger than denominator power, it's 3 minus 2 in the numerator. I mean, in the power here, right? In the numerator. So that means we had 3 in the numerator, 2 in the denominator in multiplication, and what survived is to the power of 1. If you want this law to still be true, then what would happen if I switch? If I switch and I put it and I put here 2, and here I put a 3, guys. Yes, I put a 3 here. So it's 2 times 2, and here we have 2 times 2 times 2. Yes, what do we get? We get cancellation, and we are left with 1 over 2. And if I want the law to hold, that would be 2 to the power of 2 minus 3. Are you with me? Yes? Very good. I got it. Yeah, so you understand how it goes, right? The narration, it's just the symbols, they start meaning something. So I now see why 2 to the power of -1 equals to 1 over 2. Because that means the -1 power just means 2 survived. 1, this means to me what? 1, 2 survived after battle in my denominator. Yes? If I see a positive power, that means that that this many 2 survived in the numerator. Yes? So very quickly, then what is 2 to the 0? That means what regarding survival? How many 2 survived?
0 of them survive.
Sorry?
Oh no, well, Never mind. I'm sorry.
No, don't be. I just didn't hear what you said, right? What did you say?
No, I thought if because you did the same thing, so you was trying to teach y is a 0, right? So if it's 2 to the second power over 2 to the second power, right? That would
Yes.
still be 2. That's still 2 to the 0, right? And then if you like if you
Yes,
do it even
that's
more,
exactly right. So the answer will be, what is 2 to the 0?
it's it would still be 0. No, it still be 1. I'm sorry. It will be
Not still, but you don't need to use the word still, but you're absolutely correct. It will be 1. Yes, James, you got it. It will be 1 because that means that that no 2 survived, right? That means what? Look at it again, guys. Right? 2 to the 0 can be written as, for example, you can prefer to make it to anything. It can be 2 to the power of 2 minus 2, right? It doesn't matter. That means that the numerator gang and the denominator gang, right? They died out. They killed each other in a shootout. They annihilate one another in a shootout, right? So division, we have 2 times 2, 2 times 2. Yes? Good? You understand, guys? The only reason I understand some of those things a little better than some of you is because they are not meaningless to me, right? I just right away connect it you might say the connection is rather just awkward, but it doesn't matter, right? It just right away can see many things with it. So they are all canceled out, and I get 1. Okay, guys? Now, one reason we are so slow, since we're talking about 1, one reason that we're slow is that you understand theoretically all of this thing is something you knew from previous material, from previous classes or whatnot, right? But we in practice do not know that. Many of you do not know this material. So stay for office hours when you are not good in math, for sure, right? And not good meaning maybe you're good in thinking, but you do not know enough. Good? It's 1. Understood, guys? So it's 1. Now, last question. What is 0 to the power of 0? 0 to the power of 0, guys. What is that going to be? So some people say, and some say 1. One person say D and it does not exist. Depends what Pavel says. 1. Look at it by this analogy, right? Could we possibly have a gang of 0 in the numerator, let's say to the power of 3, divided by a gang of 0 in the denominator? Could that possibly work? Undefined. Undefined. Because 0 to the 0, it means, what do you mean? There was a gang of zeros in the denominator? Come on, what do you say that? What's your slang? I'm not sure today. You hear me, dog? Zeros in the denominator? Are you kidding me? Well, I don't think calculators say 1. If you take 0 to the power of 0, and I'm not sure how the calculator is programmed. The calculator is not your teacher. I'm your teacher. And do not, you don't have to agree with me that it's not defined. Maybe you can come up with a definition. What I'm saying is that this interpretation of having a gang of zeros in the denominator does not make sense. And it should not make sense because you understand why you cannot divide by 0, not because some teacher tells you, oh, you cannot divide by 0. Bad things will happen to you if you divide by 0, right? No. You risk it. You ask, why not? Let me try to risk it. Will something bad happen to me, right? Or not? Right? It has to be here, guys, right? It has to make sense. Okay, good. So with some effort, yeah, perhaps, Christian, right? There are many things where you have other notions. You see, what mathematics is when it's exciting is when you are allowing your imagination to take wings. It's like a dove that flies in vacuum. Good. So with some effort, you can possibly justify that just given any real numbers as the powers of a to the x times a to the y is equal to a to the x plus y. That's the exponent law of addition, right? It's not obviously true from this property. You understand? This is just for positive integers, but with some effort, you can say that can be justified. So Dante, you're saying, so if it was anything but 0 to the power of 0, it would be 1. Yes. All right. As long so yes, that would be. Usually, you prefer to work with positive numbers, but that's all an entire story, right? And don't remember it as a conditional, right? You're not trying to answer You're not trying to respond to me. You're trying to understand it, okay? So, okay, guys, we are now trying to figure out what you remember, some people dropped the x, and that was incorrect. At least maybe it is correct, but definitely it does not follow from the exponent law. If you understood it, you don't use that shortcut, okay? So here is my function, f of x equals to a to the x. Nassim, you look very interesting. You look like somebody from a 20s movie that somebody colored. I really enjoyed it. It's like I'm watching an old good film. Sorry, I had to say that. So
I'm sorry, I still at work today. So
no. It was not. You know, I just look at it. I'm thinking it's interesting. I'm watching a colored documentary from the 1920s. So here, good. Are you there, guys? So a to the x. A to the x. How do I take the derivative? This is the first time where I actually prefer my second notation. This one with the h. Okay. So I try to take the derivative, guys. Look at it. Look very carefully. Are you ready for the magic? I take the derivative, and what I do, I plug x plus h into the function. I subtract the function at x, divide by h. Here is what I get. Agreed? Everybody sees it? Now, because I have this exponent powers, which we'll pretend we understand them for a moment. Okay, you see this? A to the x, a to the h, I am able to factor it. I'm going from here to here, yes? And then I can factor out a to the x. You see, in other words, this is because it does not, the x is here not affected by the limit. Don't go on the sim, I enjoy it. So h going to 0, yes? Yes, guys? Now, watch very carefully. What is this, guys? Look at it. It's a to the x. You understand how I go through the limit? Blah, 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 blah. The a to the x is constant relative to h, so I can factor it out. In other words, it's the limit. Look at it. It's the limit as h goes to 0 of a to the x times this limit. Yes, it's limit of a product. So here I put in a red circle. What is this? And by what is this, I mean something deep, guys. Do you recognize what was happening here in words? Let me give you a hint. You began if you look at this formula, so you look at this formula and you ask me this question, what is this? I said somebody is trying to take the derivative of a to the of the exponential function with base a at the point x. That's how I answer this question. You understand? When somebody asks me what is this, I don't give him the procedure, oh, this is 7 or something like that, right? No, what is happening here? What is somebody trying to accomplish here? What is this? You understand my question, guys, right? I'm asking you for your very basic recognition. Well, we're trying to do something here, right? And one important thing that many people are missing is that they are just trying to calculate a way they're trying to do, but they don't stop and reflect on what is it that they are doing. So I'm asking, what is this? Derivative at 0, June. You got me perfectly. It is the derivative at 0. Are you with me, guys? The rest of you? This is no. That's why I try to teach you the definition. I'm trying to teach you to read it, right, and think about the meaning rather than what an answer is. Exactly, Brandon, right? Because x is equal to 0. Look at it. What's happening here? For this derivative function, look at it. The limit that we're dealing with, my point is going to be this. The limit I'm dealing with is actually one that you cannot so simply deal away with. It's not like the previous limits where we actually solved them, right? It's one where you need another point of view, another strategy altogether. It's like this, you see. So you you see a ram, what is the way that a ram is dealing, or a bull? The way a bull is dealing with a problem is right, and it charges right into it, and of course the bull is very strong, and the bull can crush many things, but not if it's a metal pole. If it's too hard, the bull is going to break his skull, even a bull. Do you understand? So what you do is you realize, first of all, what is this thing, rather than just charge at it. And here is how you look at it. Look at it. We are zooming in. Look at it. We are zooming in at some arbitrary point x and trying to calculate slope at that point. Right? We're zooming in. We're hoping we will see a straight line segment, and we hope to calculate the slope of that said line segment. But using this calculation, do you see how it happens? Look at the magic, right? I'm able to suddenly see that I don't in fact need to zoom in the point x. The entire thing is decided when I zoom in at 0. You understand? Normally that does not happen, but here the function is differentiable as long as it's differentiable at 0. If and only if it's differentiable at 0. Do you follow? Are you with me, guys? Right? So you will see how I bypass this metal pole. Okay? So I'm not going to charge it. I'm not going to try to solve this limit. I'm actually going to do, hopefully today we'll finish this entire discussion. I'm actually going to bypass this obstacle by pretending that I was able to break it. You understand? It's too hard for me to break with my horns. I'm going to bypass it and pretend that I figured how to deal with it. And here is how I do that. Look at it. If this limit exists, look at it. If this limit exists, is the derivative of my function at 0. Do you see that? Look at it. The derivative of a to the x is a to the x times the derivative of this function at 0 times some number. Yes? You understand what I do? Pavel, you shook your head. You didn't understand. Do you understand what I mean now? I did not figure what this number is. I just realized the form, right? The pattern of this derivative will be the original function multiplied by some scalar. Because if the derivative at 0 exists, this thing, which I haven't figured out to calculate, will just be a number. So it will be the function multiplied by some number. That's what I'm trying to say. You understand how you think? That's a very kind of, it's an entirely different point of view. In fact, if you paid attention, you do it all the time. When you are solving, let's say, when you're solving this equation, right? Let me just verify how you think of it, okay? You might have not realized it, but you were doing it all the time. So suppose that I'm asking you to solve x squared equal to 5, right? In your high school, what did you say x equal to? X squared equal to 5. What value of x did you give? Simple thing, type in your answer. If you, of course, figured out to solve it in high school, right? I mean, you got what, some score for it. They said, wow, teacher said, wonderful, you solved this thing, right? What was that thing that you solved? Well, Christian, you're using a calculator, my dear. And that's also not the right answer. Exactly, radical 5. Okay? Calculator is just another thing, right? But you would say maybe plus or minus radical 5. Do you understand what you actually did? What is radical 5? How is it radical 5? Well, first of all, what is that radical 5 about? Radical 5, it means what? It means a number that if multiplied by itself gives you 5. It doesn't change anything. Look at it. Here I called it with x. Here I gave it a nice name. What is this? It's just, it says, it's some number that if you multiply it by itself, you get 5. Isn't it? This is saying a number multiplied by itself is 5. Have you solved it? No. You just gave a name to this unknown that you don't understand, right? How to do. Why is it different? For example, if I said x squared equal to 25, again, it seems that a number x equal to plus or minus 5, this is somewhat clearer to us, right? We have a much more direct meaning of this value. Yes? Do you understand the difference? Look at it here. It feels like I solved this. And if you think about the top equation, it feels like I pretended that I solved it because think about deeply. If you cannot calculate root of 5 without your calculator, right? Doesn't matter that you have this machine. This machine was not available to people that invented calculus, and was not available to Babylonians, and was not available for thousands of years. Yes? What is this answer? It just means you pretend you solved it. You bypass the problem. That's what it is. You understand? And if you bypass the problem and you're smart about it, you can in fact actually later on figure what it is, what's the solution, as I will show you today. Okay, so much in mathematics involves not to attack the problem, but to figure out how to bypass it. So you have a giant guarding the gates, and you cannot tackle the giant. He's too big, he's too strong, there is nothing you can do about him. Maybe you can outrun, go around him, and sneak through the gate, but you don't find the giant. Clear? So we do it the same thing, just like you do not know. And if you know, then without a calculator, you can give me an approximation of root of 5. If you use a calculator for it, that means you do not know. Right? So yes, makes sense? Good. So this is what we do here, right? So here, I also bypass the problem, just like I did before. I just give it a different name. I say the derivative at 0. I assume that the answer exists, and I assume, and I know based on the form, simply by form, this is the derivative at 0. That's what is calculated here. Yes? Now, let's try to make you a little bit more comfortable with this entire thing. Let's hope that I can. So first of all, what it tells me is this. First observation. If I take the derivative once, I get back the same function multiplied by some scalar. Now if I take the derivative again, the derivative bypasses the scalar. And again, I have another scalar popping out. So it will be f prime of 0 squared times a to the x, right? I just end up, when I take more derivatives, I end up raising that number to some power. Do you understand what I'm saying? Yes, guys? It's very important. You see, it's an entirely different way of thinking that we're trying to develop here. We are bypassing the problem, not solving it. Now, you are still uncomfortable and you like calculators. So let us actually get a sense of what that number might be. Okay, so let's suppose that we're dealing with derivative of 2. We wanted to take derivative of 2 to the x, yes? And then we end up figuring what's the derivative of 2 to the x when x happens to be 0. That's the limit, right? It's 2 to the 0 plus h minus 2 to the 0, which I write as 1, divided by h. Now, if I do not know how to take the limit directly, I can think, well, the derivative will be well approximated by plugging in a small value of h. Because what does it mean? It means that as I get better and better approximation of 0, I'll get better and better approximation of the derivative. So if I cannot get better and better approximation, let me pick some approximation. Let me pick, for example, if h is small, let me pick 0.001 instead of h. Yes? So I say, well, the derivative will be possibly something like 2 to the power of 0.001 minus 1 over 0.001. And if I plug this information in my calculator, I get something like 0.69. So this number looks somewhat like 0.69. At least that's what my calculator is saying. Right, guys? I do not know why it makes you feel more comfortable or make you believe that you understood it better, because if you don't know what the calculator is doing, you don't understand anything better, but be my guess. That's roughly the number. Okay, so that means that the derivative of 2 to the x is roughly 0.69 times 2 to the x. And if I take nth derivative of 2 to the x, that will be 0.69 to the power of n times 2 to the x. Do you understand why? So here again, look at it, guys. Just to be sure. 2 to the x, I take the derivative. That will be approximately 0.69. Let's pretend that's actually the true number, multiplied by 2 to the x. Yes? When I take the derivative, again, the derivative bypasses the scalar. So it will be 0.69 multiplied by 0.69 times 2 to the x. Yeah? Which would be to the 0.69 squared. You understand? So in essence, the function is not too affected by differentiation. It's just the original function, but you multiply by an extra scalar, I'm sorry. Good. Now, what happens if I do the same procedure with 3? Look at it, right? Using my calculator, I plug 0.001 instead of h and hope that that's small enough. That means h is close enough to 0 to give me an approximation of what the derivative is. And notice it is 1.099. Yes. So then I expect that the derivative of 3 to the x will be approximately 1.099 times 3 to the x. Here is quick comprehension check, guys. Please do it as fast as possible. I want you to estimate the derivative of 2.8 to the power of x. You see that? It's 2 to the 2.8. I want you to tell me what roughly will be the derivative. You can use your calculator to carry out this estimation. Okay, Minkowski, good. What about the rest of you guys? Figured it out? I need to see that you followed this entire idea. Well, Brandon, if you're using something else, make sure that you understand why that works. That's something else, right? I mean, you can memorize all sorts of things. Why does it work? Do you really understand it? That's the goal here. Come on, come on, come on. You understand using what I explained, guys, right? Because who knows how, some of you took calculus before, but one thing about it is that you can just calculate things without understanding what those things are at all. That's not what I want. Okay, let's go through it. Okay, so what do we need? We need to know the limit at 0. You understand? It happens that the derivative at 0 is all deciding. Now the derivative at 0, I have no idea how to calculate right now directly. Yes. So what I do, I hope that's just hope, guys. You understand? It's all hope. I plug in small h, which I think would say 1/1000 or 0.001. I imagine it's small enough for my purposes. Yes. And there was no reason for it. I just decided it's small enough, right? It's arbitrary. Maybe it's not small enough. I plug it in, and in your calculator, when you carry out the calculation, you get roughly 1.03. Yes? So that means that the derivative of 2.8 to the power of x is roughly 1.03 times 2.8 to the power of x. Okay, so here is an important remark. We have cheated a little, or in my opinion, quite a lot, because you are using a calculator. What is your calculator truly doing? When you take 2 to the power of 0.001, your calculator is calculating perhaps the 1,000th root of 2. Do you even know how to calculate without a calculator the square root of 2? Right? And I don't need you to carry the process. Maybe the process is tedious, but if you do not have a way to get at it, that means that you're completely blind to it. You don't know how to carry this calculation. Okay? You understand, guys, what am I saying? I'm not sure if it crosses you, right? So somebody programmed the calculator. If it were somebody like me, I could program it to be giving you false information. Right? And not only that, I mean, false or not, if you do not understand that, then you don't have a deep connection to the subject. You don't know it. Maybe somebody does, but not you. Right? Good. So here is what we have observed. So the derivative of 2 to the x is roughly 0.69, which I called c sub 2. It's some constant that relates to 2. If I take the derivative of 3, it's some constant that relates to 3. So I call it c sub 3. And in general, when I take the derivative of a to the x, if the derivative at 0 exists, which I haven't verified, it will be a constant that relates to the number a times a to the power of x. What will be the simplest possible constant you can hope for? You see, we have those numbers, and simplest, of course, when you take repeated derivatives, it can be complicated, right? If I take many derivatives, I have to multiply this number by itself. So multiplying 0.69 by itself is not that easy if I want the number, right? So what's the simplest possible value I can hope for? June says 1. What about the rest of you? What do you think? You understand my question, right? So here you take the derivative of 2 and you get some number that's not so nice. You get derivatives of 3 to the x, you get some other number. You can play around with your calculator and see what sort of numbers you might be able to achieve. And the question is, what is the simplest possible number you hope for? If I gave you this on the exam and I told you cannot use a calculator, right? And I told you calculate the derivative of a to the x to correct within 2 decimal places, take the 100 derivative, 100, right? But you can choose your base, right? What base would you have preferred? You don't need to tell me the actual base, but you would have preferred what to happen? What would you like this constant to have been? Is my question clear? Brandon says something interesting as well. Brandon says 0. Keep it in mind. Wonderful, Brandon. Thank you for your comment. 0 is what Brandon says. What about the rest of you guys? Don't you have preference? So Alan says 0.5. Can you, if you say that, Alan, can you tell me what is 1/2 to the power of 12 right away? So Zohab says 1. David says 10. Think about it. If you think 10 is an easy number, can you multiply 10 to the power of 4? You might write some answer to it, but be careful, right? 10 to the some power. The question is, of course, what do you mean by calculate? Just small, a whole number, that's already something, but which whole number? You see, if I get the derivative of some a, if I have the derivative of some a to the x, let's say it is 2 times a to the x. Am I happy with that? Well, think about it. Take more derivatives of that expression. So more derivatives, take another derivative. So take a to the x and take, let's say, 17 derivatives. That would be 2 to the power of 17 times a to the x. Presumably you want to calculate to the power of 17. You understand? You understand what I mean by complexity, right? So you see what number pops out. If something pops out, it makes it more complicated. So you have to have a sense for such things. If you have a sense for them, you know what you are seeking. And if you know what you are seeking, it's not arbitrary. Otherwise, you're walking in a forest, and if you try to get out of a forest and you do not have a bearing, you don't have that reckoning, you will be going in circles because one of your legs is stronger. That's a fact. You will go in circles and you starve to death, or a bear eats you. You know, I remember from Chekhov, he never had time to scream when a bear came and sat on him. That's my translation. I'm pretty proud of it. No, no laughter. Too tired. Okay, I'm not suggesting. I am asking you what's the best. Right? I did not suggest anything just yet. If I want your instincts, I want you to be alive. What is it that you want? If you don't know what you want, then you don't get anything. And you need to know precisely what is it that you want. So Hailey D says 0 or 1. Wonderful. Okay. So some of you have some sense. Some of you say 0 or 1. So let's try to investigate. We're dealing with exponential function. Can we possibly have 0? Can we possibly get 0? So 0, clearly, if a 0 pops in front, then that annihilates the function to 0. It's very easy. 0, derivative of 0 is just 0. Very easy number. Yes? Can derivative of exponential function be 0? Because look at it. The derivative of the exponential function at 0 multiplies the exponential function. And that gives you the derivative anywhere, at any x. Yes? Could it possibly be equal to 0? If the derivative is equal to 0, then what do you have? Derivative equal to 0, you right away see line, horizontal line. Yes? Horizontal line as the graph of your function means what? It means that the function is constant. No matter what's the x, it's constant. But is a to the x a constant function? If a is not 0, could it possibly be a constant function? It's not that it's not allowed. It's just my question is simple question. Can an exponential function be constant? 2 to the power of 1, 2 to the power of 2, are they the same? That's not a constant function, yes? Very simple. 2 to the power of 1, 2 to the power of 2, to the power of 3, not the same. Take any number that's not 0. When you multiply it by itself, other than 1, of course, 1 to the power of x also not interesting, right? So a is not equal to 0 or 1. When you multiply a by itself, you do not get constant, right? It changes. Multiply a number by itself, you don't get the same thing. Do you follow me, guys? You see, my brain is overheating, but hopefully not yours because it's such an easy thing, right? If you just picture what you're doing, it cannot be a constant. Therefore, Brandon and people that suggested 0, that was a great, brave suggestion, but it's impossible because we are dealing with non-constant function. So our best choice is to hope for 1. Do you agree? Do you agree because I badger you, or do you agree because you understand, guys, right? It has to be dead reckoning. Do you follow what we're doing here? So if I found, look what I'm hoping for, right? If there is going to be some number which I call e, the derivative of e to the x will be the derivative of the function at 0, which I hope to be 1, and that will be just e to the x. The derivative of the function is itself, nothing changed. So derivative is not affecting it, if I can get the 1. Okay, and it appears by those calculator games that this number e might be lying between 2 and 3. 3 gave us 1.0 something, right? 3 I think, or something like that. And 2 gave us 0.69. Yes? So 2 was too small, 3 was too big. So we hope e will be like this Goldilocks number, just right. And of course, the number e will have to satisfy this limit. Limit as h goes to 0 of e to the h minus 1 over h equals to 1, because that's the definition of the derivative of this function at 0. Yes? So what we are doing now, guys, here is what I'm saying. We are not searching for a solution to a problem. We are searching for a problem that solves to 1, right? We have the solution. We are searching for the problem. That's the different thinking here. Yes? Do you understand? So again, the function e to the x is the most significant function in mathematics, definitely one of them. And we are going to talk about it now in some detail, as much as we have time. So here is what we carried out in this previous section, the brief review. Are you with me, guys? If I try to carry out the derivative of a to the x, I realize using the second definition, that's the first time I prefer notation number 2, because here I do like to factor, you see? It would be, this is the definition of the derivative at x. I break it apart, I'm able to factor out a to the x. You see this? A to the x does not depend on h. And I end up calculating the derivative at 0. You see, I started calculating a derivative at an arbitrary point, but I end up calculating it at 0. And if this limit exists, its derivative at 0 is some number which I call f prime 0. I just notice the form of it. So I don't solve the problem, but I notice the pattern is that the derivative of this function will have to be the function multiplied by some scalar. And that scalar cannot possibly be equal to 0, because that would imply the function is constant. If it's 0, the function is flat. That means that for every x, I get the same value. But let's say 2 to the x when x is 1 is 2. 2 to the x when x is 2 is 4. You understand? Exponential functions are not constant. Right? Aside from trivial examples, which do not necessarily mean much, 1 to the x or 0 to the x, right? So aside from trivial bases, that was not going to be useful. And then we carried out estimates for derivative of 2 at 0 and derivative of 3 to the x at x equal to 0. We carried out estimates and we saw that the estimate for 2 is short of 1. The estimate of for 3 to the x is slightly over 1. And we are hoping that there will be a value, just again, right? There will be a value that will solve to be exactly 1, which is e to the x minus 1 over h. We hope that there is a number, that's hypothesis, that such a number will exist, okay? Good? You understand how I got my hypothesis, guys? And you understand why when I solved this limit, I actually still cheated, because I estimated what's the 1000th root. And how did I do that? If you do not know how to estimate roots, then you use something that you don't know. Good? So here is what's true in mathematics. Here is now because I believed I bypassed the problem, I can actually figure out how to solve this problem without the calculator, without anything. Are you ready? So that's, if you ever ask yourself, does Santa Claus exist? Have you asked yourself that question? I mean, if you were Christian, I'm not sure, or if not, do elves exist? And the reason some of you say they do not exist is because you don't believe in them. And in mathematics, as in life, you actually see that monsters or whatever creatures, they exist because of your belief. They actually physically, or I'm not sure if that's physical, but they exist. And I would like to show you the sense in which they do. Okay, so I do not understand anything about e to the x. I don't understand much about exponentials. And when I think about it deeper, I realize here is what I'm seeking. All right, the derivative of the e to the x function will be e to the x if such a thing exists. In other words, it's a function whose derivative equals to the function itself. Derivatives don't do anything to this function, right? It's impervious to derivatives. So I try to solve this differential equation. Find me a function whose derivative equals to the original function. Makes sense? And I add up this extra condition. Because exponentials, right? This is because, let's say, e to the 0, I suppose it will be equal to 1, as we discussed. 2 to the 0 is equal 1, and 3 to the 0 equals 1, right? So I add this extra condition. I want it to equal to 1 at 0. And I want to solve all functions that satisfy this property, okay? If this is uncomfortable for you, you can still somewhat think of e to the x. I'm not sure what's your comfort level and what is it that you believe in and what is it that not. Why do you think that if something is written in a number that makes it real more so than if it's not? I don't know. Good. So here is a very important first question in that direction, guys. Could the function satisfying this differential equation be a polynomial? In other words, could there be a polynomial whose derivative equals to itself? First of all, do you remember what polynomials are? What is it that I'm asking you? Another thing to think about is e to the x a polynomial? Is 2 to the power of x a polynomial? If you don't like e, right? 2 is more definite to you. So is 2 to the power of x? Is it poly? Is it a polynomial? You understand what first of all, do you understand my question? I used a very lofty word, polynomial. What am I asking you? Right? If they don't understand the word, of course, how can you answer this, right? Is it profsoldific? Meaningless, right? I can say, what is that? I'm asking, is 2 to the power of x a polynomial? And before you answer this question, you think about it, scratch your head for a moment and ask yourself, wait a minute, do I know what is a polynomial? Because otherwise this question is meaningless to me. What's a polynomial, first of all, please?
It's written in terms of addition and multiplication.
Beautiful, Carolina. It's an operation that I can carry out using addition and multiplication, right? So let's say about 2, right? So if I have, say, 2 cubed, right? 2 cubed is 2 times 2 times 2, yes? So I can carry out 2 cubed in terms of multiplication. Isn't it nice? Well, any problems? What about 2 to the power of 5? Well, that's 2 times 2 times 2 times 2 times 2. Right? I did not carry out the same number of multiplications. If you think about a polynomial, it means that I process by the same multiplication and division, so the same multiplication and addition set every particular input. Make sense? So when you think of a polynomial, what do you think? It's a function that uses only addition and multiplication, but another thing to mention about it, that's why they define it the way it is that, for example, here is a polynomial. What it means is what? It means that I have 5 plus 7 times input minus input squared. You understand there is no x. When you think say x, it's a bit, you forget what's the meaning. The meaning is that there is this digestive process of the input, and that digestive process uses only addition and multiplication, and it uses in some sense the same addition and multiplication, the same procedures, right? Whereas let's say if I have 2 squared, I multiply just 2 by itself 2 times. 2 cubed, I multiply 2 by itself 3 times. So just by that, it's and then also there are other problems. Okay, so be careful, of course. I'm not asking you to tell me yes or no right away. I first ask you to understand what's the question. The question is extremely important. If you understand what the question is, you are already way ahead of many of your people. Right? So what's the question, right? The question is whether or not we can simulate, and here it is, right? So here e cubed, it uses multiplication, but there is also other problems. E to the 1/2, for example, would be the root of e, and roots, I do not know what I mean. And even worse, I have e to the power of root of 2. What is that even at all? What does it mean? Yes? So let's begin trying to investigate whether or not e to the x, again, it's this mythical, it's a unicorn for now, right? We don't know, we hope it exists. We try to believe it exists. It's some sort of thing that we have very little understanding of, but it has this mythical property that when you take derivative, it's not affecting the function. It stays the same. That's all we know about it. And that at 0, it equals to 1. Yes? That's good, Rafid, if you do, right? Then you should know it very well. Get to know your e to the x, but make sure that it's not in the biblical sense that you get to know e to the x, so your neighbors won't complain. Good? I don't think you understood my joke, guys, or maybe it was too dirty. So, yes. As in sheep, if I have to explain to you in a crass way, right? Right? To know it biblically, right? If you have it in your backyard. Good. So, but know it aside from it, right? Know it well, but again, okay? As my professor used to say, in the privacy of your bedroom. So here, let's see if it could possibly be a quadratic polynomial. Well, let's look at it. What happens to a quadratic polynomial when I take its derivative? Look at it, you see? I take the derivative of the quadratic polynomial and I get a linear. Yes? Are you with me, guys? You see this line? You see how I took the derivative? I cannot have definite numbers for a0, a1, and a2 because I don't know them. I think imagine some quadratic polynomial could be e to the x. Well, I take the derivative once, it's linear. I take the derivative twice, it's just a constant. Take the derivative 3 times, it's 0. But e to the x, when I take one derivative, it's the same. When I take 2 derivatives, it's the same. 3 derivatives, it's the same. And it's definitely not constant. So it could not possibly be a quadratic here. Do you follow? Now, next question, could it possibly, so e to the x, I right away know it cannot be simulated using quadratic polynomials. Could e to the x be simulated using cubic polynomials? You understand what I did? I know my polynomials. I know properties about them. And I know just a few properties about e to the x. And I compare whether or not they have the same property. Namely, do they change under differentiation? E to the x does not change under differentiation. That's the property it has, right? And polynomials, quadratic polynomials seems to change under differentiation. And I do it I reduce it to absurdity, because that's why I carry the derivative to 0, because it's very obvious that e to the x is not 0. Yes? I try to make it simple. So could e to the x be a cubic polynomial, guys? Are you there with me? You get it, Pavel, what we're doing? Yes, Pavel, you get it? Alisa, do you get it? Who else is there? Right? You follow what's happening? Great. It's a very, I hope you would just see what we're getting, right? Just because I imagine this thing, I can actually suddenly see its property. It's going to become more and more real. So could it possibly be a cubic polynomial?
I'm sorry, but you just said that e to the x it can't equals to the a0 plus a1 x plus. So I don't.
Quadratic.
Yeah,
This all I'm saying here is that if you're using polynomials up to degree 2, you will never be successful in capturing e to the x. It will not be among those polynomials where the degree is at most 2.
then
I'm asking if I add and I make a degree cube, I add more flexibility. In other words, a3 can be 0, then it's a quadratic, but I don't have to make a3 equal to 0. So if I add the possibility of using x cubed there, could I simulate what e to the x is?
I mean, if if it can work with the quad 3, then I guess you can call it a certain function or a polynomial, I guess.
Well,
But
if it does, so my question is, does it work with polynomial 3? In other words, would e to the x end up being a cubic polynomial? That's the question. Guys, you understand the question, right? I hope you're not lost and not to see where is it headed, right? I like polynomials. Why? Because I know much about them. I know how they digest their inputs. I know exactly what's happening to them because I'm so familiar with addition and multiplication. If you study programming, then you might have realized that computers are only able to do addition. And through addition, you can simulate multiplication, right? So polynomials are certain things that maybe are much familiar to the computer. So my question is, could it possibly be polynomial of degree 3? Why or why not?
wait, doesn't q squared make a whole line?
Sorry,
It's the
if what?
doesn't you said could e to the x power equivalent to this, right? So doesn't ex, so doesn't it make it, doesn't q squared make it into a line, right? And
Where?
no, in the
It's squared. So in general, I'm asking, could e to the x equal to a cubic polynomial? Could, for example, do you understand what I'm asking? I'm asking for any arbitrary values here. So for example, maybe could e to the x be possibly the polynomial 3 minus 7x plus 12x squared plus 100x cubed? But the numbers here are arbitrary. I'm asking right away, could it be any combination like this, where this is a number plus a number times x plus a number times x squared plus a number times x cubed? I'm trying to capture a very simply understood mechanism, a formula, right, for e to the x, for how it processes. I'm trying to identify this thing. This is a unicorn again, right? We just have our imagination to believe it exists. We were not able to calculate any of the limits before, if you remember. So guys, let's finish this, so then you can decide if, and some already left. My God. How can you live at this moment, right? You're watching magic and you can go. I don't know. So guys, could it be cube? Could it be a cubic polynomial? It's all such a simple question. Okay. I don't know. I don't see why you don't see it, but so you say yes. Okay, let's see yes or not. Okay, well, let's see what happens. E to the x, the only thing I know about it is that if I take derivative, it doesn't change, right? Let's take a cubic polynomial. Take one derivative, it becomes this. Can you see? You see this, guys? To take a derivative of the cubic polynomial, and it's reduced to degree 2 polynomial. Yes? Take the derivative again, it's reduced to a linear polynomial. Do you understand how to take the derivative? You just can do it very quickly, yes? Take the derivative again, it's constant. Take the derivative to the 4th power, and it's 0. But the derivative of e to the x again and again is e to the x. Do you understand what I see? I see a difference between a cubic polynomial and e to the x. The polynomial degenerates to 0. E to the x does not degenerate. So they cannot be the same thing, because there is a difference between the property that you observe in one object, in all of them, in the family of cubic polynomials, which you do not observe in e to the x. Do you follow? Exactly, Rafid. It simply cannot be a polynomial, because here, let's finish it. Let's finish it here. Look at it. What if it's a polynomial of degree n? If it's a polynomial of degree n, yes, e to the x will always remain the same, but the polynomial of degree n will vanish to 0 after n plus 1 derivatives, right? You take the derivative until x to the n disappears. Everything else will disappear prior to it. So, so it cannot be a finite polynomial. Do you understand how I realized this without any algebra or anything like this? I realized they don't have the same property. It cannot possibly be a polynomial. Or could it? Right? It cannot be a finite polynomial. Think about it, guys. It cannot be a finite polynomial. So can you imagine where we're headed with it? It cannot be a finite polynomial because finite polynomials are annihilated after, let's say if it's degree n, it's annihilated after n derivatives. E to the x is never annihilated. So can you imagine what would be the next step? Think about it for next class. That's where we continue. I would be happy to know that your accumulator does not disappear. Thank you, Pavel. Right, that it doesn't disappear. Now we can rest a little bit if you are staying with me and continue talking about something else, right? About the questions that you solved or some ideas that you could come up with. Logarithms, for example, we need to review. So I stopped.